Hello friends, welcome to my lecture on isomorphic and homeomorphic graphs. Let us first discuss Königsberg problem, bridge problem. The 18th century East Prussian town of Königsberg included two islands, this island A, the island B, okay, and 7 bridges shown here in this figure 1, 2, 3, 4, 5, 6, 7. So, there are 7 bridges, okay, and we have two towns A and B, and C and D are the river banks. This is the river. In the river there are two islands A and B, there are 7 bridges and the river banks are C and D. So, the problem is beginning anywhere and ending anywhere, can a person walk through the town crossing all 7 bridges, but not crossing any bridge twice. Okay. This problem was asked to Swiss mathematician L. Euler about the people of by the people of Königsberg, and then Euler in 1736 proved that such a walk is impossible. He replaced the island by means of points the C and D, okay, and the two sides islands by means of points A and B. Okay. He represented islands by means of points A and B, and the two sides of the river by means of points C and D, and the bridges he represented by curves. Okay. Then he obtained this graph. Okay. This graph he obtained. So, in this graph we can see that all the vertices of this graph A, B, C, D have odd degrees. Okay. Degree of C is equal to 3, degree of A is equal to 5, degree of B is equal to 3, degree of D is equal to 3. So, all the vertices have odd degrees, and therefore, this graph is not traversable. Thus, one cannot walk through Königsberg so that each bridge is crossed exactly once. Okay. Now, isomorphic and homeomorphic graphs. Suppose GB and G star, B star, E star are graphs, and F is a one mapping from B to B star between the sets of vertices B and B star, such that UB is an edge of G if and only if FU FB is an edge of G star. Okay. Then F is called an isomorphism between G and G star, and G and G star are called isomorphic graphs. Let us also see the definition of homeomorphic graphs. Given any graph G, we can obtain a new graph by dividing an edge of G with additional vertices. Okay. Two graphs G and G star are called homeomorphic, okay, if they can be obtained from isomorphic graphs by this method. So, if we are given a graph G, okay, we can obtain a new graph by dividing an edge of G by adding vertices, okay, with additional vertices. So, two graphs G and G star are called homeomorphic if they can be obtained from isomorphic graphs by this method. Now, by this method means by adding vertices. Now, alternate definition of homeomorphic graphs: two graphs are called homeomorphic if both can be obtained from the same graph by inserting new vertices of degree 2 into its edges. Okay. So, such an operation is called an elementary subdivision. Now, let us look at the graphs G1 and G2 here. This graph G1, this graph G2. Okay. We will see that both of them are homeomorphic, because both can be obtained from the graph G3, okay, by adding a vertex to one of its edges. If you add one vertex here, okay, let us say either on this edge or on this edge of graph G3, okay. So, then you can get this graph. Okay. So, by adding one vertex either to this edge or to this edge, okay, we can arrive at this graph G1 from G3, okay, and we can arrive at the graph G2 by adding one vertex over this edge. Okay. If you add one vertex over this edge, okay, then you can get this these edges, okay, these edges, and the other edges are as such. So, this graph G2 can be obtained from G3 by adding a vertex on this edge, okay, let us say this is AB, on adding a vertex on the edge AB, and the graph G1 can be obtained by adding a vertex on the edge AC or on the edge CD. Okay. So, the graphs G1 and G2 are homeomorphic therefore. Now, let us look at this figure. Graphs A and B in the figure are not isomorphic. Now, you can see the graphs A and B are not isomorphic. Why they are not isomorphic? Okay, because we see that two graphs are isomorphic if UV is an edge in a graph G, if and only if FU FB is an edge of in the graph G dash. So, here you see this is an edge. Okay. Say this is A B. Okay. Corresponding to A B we have edge A dash B dash. Okay. Then corresponding to B C we have B dash C dash. Okay. Now, let us see here we have D. Okay. So, D E corresponding to edge D E we have D dash E dash here. Okay. Now, corresponding to the edge this one, say here we have F dash, corresponding to the edge E dash F dash. Okay. We do not have here EF. Okay. Say you take E dash F dash edge, then we do not have EF here. Okay. The vertices E and F, so that U E F corresponds to F E dash F B dash F F dash. Okay. U B is an edge if and only if F U F B is an edge. Okay. So, we do not have a function f 1 onto function f such that E f corresponds to F E F F. Okay. F E F corresponds to F F F E F F. Okay. So, this is not possible. We do not have any function f such that whenever u v is an edge, okay, of the graph A, f u f v is an edge of the graph B. So, A and B are not isomorphic. Now, let us see, they are homeomorphic because they can be obtained from the graph C by adding appropriate vertices. Now, you can see if you look at the graph C by adding vertices one vertex here, one vertex here, you can get the graph B. Okay. So, by adding two vertices on this edge, okay, on this edge we can get the graph B. So, B is can be obtained from the graph C by adding some vertices, and similarly here if you add one vertex here on this vertex on this edge, okay, and one vertex here on this edge, okay, then you get this graph. Okay. So, A and B are obtainable from the graph C by adding additional vertices, and therefore, we can say that the graphs A and B are homeomorphic. Okay. Now, let us consider the graph given in the figure below, so that they are distinct, that is no two of them are isomorphic. Now, if you can see in the graph A there are 1, 2, 3, 4, 5, 6 edges. Okay. Graph A has 6 edges, while the graph B and C have 5 edges each. Graphs B and C have you can see here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So, in the graph A there are 6 edges, while in the graph B and C there are 5 edges. So, A is not isomorphic to B and A is not isomorphic to C. So, A is not isomorphic to B and C. Okay. Now, let us see that B and C are also not isomorphic. Okay. So, what we can do, let us say these are vertices A, B, C, D, E. Okay. And these are say vertices A dash, B dash, C dash, E dash and D dash. Okay. So, then we can see AB corresponds to A dash B dash here, BC corresponds to B dash C dash here, CE corresponds to C dash E dash here, okay. CD corresponds to C dash D dash, but there is no edge corresponding to the edge ED here, okay. Corresponding to edge ED, there is no edge here, okay. So, we can say that if you consider CD goes to C dash D dash, CE goes to C dash E dash, then ED there is no edge corresponding to ED in the graph C. Similarly, if you take, say for example, let us change we can take another situation, we can consider another situation whereby we can take like this, say A, B, C, then we can consider this one, this another situation which is possible, C, D I can take here, E I can take here, then I will have. So, A dash, B dash, C dash, then we can write say D dash, okay. So, C D goes to C dash D dash and C E goes to C dash E dash, okay. Then E D, okay, or D has no edge corresponding to, there is no edge corresponding to D in the graph C. So, therefore, B and C are not isomorphic. So, since there is no edge, corresponding to ED in graph C, okay, there is no edge corresponding to ED, ED of graph B, ED of graph B, okay. There is no edge corresponding to ED in graph C, B and C are not isomorphic. Okay. But let us show that two of them are homeomorphic. Okay. So, let us see, we can consider, okay, we can see that B and C can be obtained. Okay. Let us see, we can let us consider these graphs. This one graph. Okay. So, now another one is first of all we see that these two graphs are isomorphic. Let us consider this. Okay. First we show that this graph and this graph are isomorphic. Say this is A, B, C, D. Okay. Then what we will have? So, C goes to, this is C dash. Okay. C has degree 2 here. So, here C dash has degree 2. Okay. And then here B has degree 2. So, this is B dash we can take, and then D. Okay. So, D has degree 2. So, I can write it as D dash, and then A has degree 1. So, I can write this as A dash. Okay. So, let us consider these two graphs, then we can see that there is a one correspondence. Okay. We can define a mapping F, okay, where F is F A goes to A dash, okay, F B goes to B dash, F C goes to C dash, F D goes to D dash. Okay. A dash, here A has degree 1 here, here A dash has degree 1, here B has degree 3, okay, B has degree 3. Oh, okay, okay. So, not like this, this should be B dash here, the degree should be same. So, this is B dash, and there we shall have C dash. Okay. C has degree 2 there. So, here C dash has degree 2, here B has degree 3. So, B dash has degree 3, okay. D has degree 2 here. So, D dash has degree 2 here. So, we can define mapping F which takes A to A dash, B to B dash, C to C dash, D to D dash, and F is a 1 1 onto mapping. Okay. So, these two graphs are isomorphic, and we can see that this graph and this graph can be obtained from these two graphs by taking additional vertices. Okay. So, what we do, you take an additional vertex here. Okay. If you take an additional vertex on AB, then you will get this graph. Okay. This you can this will graph will give us this one. Okay. This additional vertex will correspond to this one. Okay. So, when we take an additional vertex on the edge AB in this graph, we get this graph. Okay. And here if we take an additional vertex on this B dash D dash, okay, then we will get this graph. Okay. So, the graphs B and C can be obtained from two isomorphic graphs, okay, by taking appropriate vertices, and therefore we can conclude that the graphs B and C here are homeomorphic. Now, let us consider this result. Let G be a connected planar graph, not multi-graph. Okay. Let G be a connected planar graph, not multi-graph, with P vertices and Q edges. Okay. Where P is greater than or equal to 3, then Q is less than or equal to 3 P minus 6. So, let us prove this theorem. Let R be the number of regions in this connected planar graph. Then by Euler's theorem, Euler's formula, P minus Q plus R is equal to 2. Okay. Now, since sum of the degrees, okay, sum of the degrees of the regions is equal to twice the number of vertices, we get sum of the degrees of the regions equal to 2 Q, okay, because Q is the number of vertices here, P is the P is the number of vertices, Q is the number of edges, twice Q, number of edges. Sum of the degrees of the regions is equal to twice number of edges. So, we get sum of the degrees of the regions equal to 2 Q. Okay. Now, we, since each region has degree 3 or more, we know that each region has degree 3 or more. Okay. It follows that two Q is greater than or equal to 3 R. Okay. There are R regions, the degree of a region can be 3 or more. Okay. So, and total degree is equal to 2 Q. So, 2 Q is greater than or equal to 3 R. Okay. R is less than or equal to 2 Q by 3. Okay. Now, let us consider this equation, P minus Q plus R equal to 2. So, we have 2 equal to P minus Q plus R, and R is less than or equal to 2 Q by 3. So, P minus Q plus 2 Q by 3, and this gives you 3 P minus Q divided by 3. Okay. So, that means 6 is less than or equal to 3 P minus Q, or we can say Q is less than or equal to 3 P minus 6. Okay. So, if G is a connected planar graph, not multi-graph, with P vertices and Q edges, where number of vertices is greater than or equal to 3, then number of edges is always less than or equal to 3p minus 6. So, this result we shall use later on. Let us consider now non-planar graphs. Let us take two examples. Okay, the example in the example A, we have a utility graph. Okay, there are three houses A1, A2, A3, okay, which are to be connected to outlets for water, gas and electricity. Okay, B1, B2, B3 as shown in this figure. Okay. Then in the figure A, we have 6 vertices and we have 9 edges. Okay. You can see 1, 2, 3, 4, 5, 6. So, 6 vertices are there, p is equal to 6 and number of edges. Each vertex is connected to every other vertex. So, 3 for A1, 3 for A2, 3 for A3. So, q equal to 9. Okay. Now, so this is now each vertex is connected, A1, A2, A3 is connected to every other vertex. So, this is the graph K33, okay, which has p equal to 6 vertices and q equal to 9 edges. Now, we have to prove that this graph is not planar graph. Okay. So, let us assume that the graph is a planar graph, then by Euler's formula, says p minus q plus r equal to 2. Okay. P equal to 6, q is equal to 9. Okay. So, we will have r equal to 5. So, if this graph is planar, by Euler formula, planar representation will have 5 regions. Okay. R will be equal to 5. Now, we can notice here that no 3 vertices, okay, you take any 3 vertices, no 3 vertices are connected to each other. Say you can take A1, A2, B1, okay, then A1 is not connected to A2, okay, A1 is connected to B1, A2 is connected to B2, but A1 is not connected to A2. So, and you can take any other 3, say A2, B2, B3 you can take, A2 is connected to B2, A2 is connected to B3, but A2 is not connected to B2 is not connected to B3. So, no 3 vertices are connected to each other and hence the degree of each region must be 4 or more. Okay. If 3 vertices are connected to each other, the degree will be 3, okay, degree of the region will be 3, but if the no 3 vertices are connected to each other, then the degree of the region must be 4 or more, and so sum of the degrees of the regions must be 20 or more, because there are 5 regions. Okay. We have seen that r is equal to 5, each region has degree 4 or more. So, sum of the degrees of the regions must be 20 or more, and therefore, the graph must have 10 or more edges. Okay. Sum of the degrees, we have seen that sum of the degrees of the regions is equal to twice the number of edges. So, sum of the degrees of the regions, if it is 20 or more, then the number of edges must be 10 or more, okay. And what we have here, number of edges are only 9. So, there is a contradiction, and therefore, the utility graph K33 is non-planar. Now, let us consider the star graph here, okay, this star graph, this one, okay. There are 1, 2, 3, 4, 5 vertices. P in graph B, p is equal to 5 and q is equal to, we have 1, 2, 3, 4, okay, and then we have here every vertex is connected to every other vertex. Okay. So, this here q is equal to number of vertices, that is equal to 10, 5 C2. Okay. This is 5 C2. Okay. So, number of vertices is equal to 10, and since each vertex is connected to every other vertex, it is a K5 graph. Now, that is, it is a complete graph K5, okay, on p equal to 5, q equal to 10. Now, let us show that this graph is not a planar graph. Suppose the graph is planar, then what we will have, let us apply the theorem which we have just now proved, this one. If the graph is planar with p vertices and q edges, then where p is greater than or equal to 3, then q is less than or equal to 3p minus 6. So, let us see what happens here. Here we have p equal to 5. So, p greater than or equal to 3 condition is satisfied, okay, and b. So, therefore, q is less than or equal to 3 p minus 6 by that theorem, okay, for a planar graph. So, here 3 p minus 6 is how much? 3 into 55 minus 6. So, that means 15 minus 6, that is 9. So, q is less than or equal to 9, but q is equal to 10. Okay. So, there is a contradiction, and therefore, the graph is K5 is and not a planar graph. That is the end of my lecture. Thank you very much for your attention.